In today's video, we are going to define Bernoulli's theorem. We are going to understand all hidden information and we are going to derive Bernoulli's equation and lot of calculations in easy way I have done here. So let's start today's topic, that is Bernoulli's theorem. In Bernoulli's theorem, we talk about fluids. Under the fluid, we can study liquids, we can study gases. But in today's video, I am going to explain you Bernoulli's theorem with the help of liquids. For example, water. And I am going to explain Bernoulli's theorem with the help of non-uniform tubular section. Before proceeding, let us understand why to study Bernoulli's equation. Bernoulli's equation gives the speed of fluid at a given point. Bernoulli's equation relates height of fluid from reference level at a given point. Bernoulli's theorem is application of work energy theorem, and Bernoulli's theorem is consistent with law of conservation of energy. So let's start today's topic, that is Bernoulli's theorem. This is a pipe and this pipe is having non-uniform cross section. At lower end more cross section and at the upper end the less cross section. You see, this region, lower part of the region is more wider and liquid start flowing from this section. So this part is more wider and the upper part is narrow. So the liquid is flowing from wider region to narrow region, and both regions are not same height, they are different height. Let us call the lower region as a C and the upper region as a D. They are not at the same height. The region C at a height H1 and the region D at height H2 compared to some horizontal reference level. Let us consider a fluid. The fluid is flowing through this pipe from lower end to upper end, from wider region to narrow region. While the liquid is flowing through this tube or through this pipe, the speed of water is not same at both ends. As fluid is flowing from wider region to narrow region. So at a narrow region, the liquid has more speed. You see, this is the narrow region and here the liquid has more speed. And at the wider region, the region C is wider. In the wider region, at wider region, liquid flows less speed. So the speed of fluid, the speed of water, or speed of any other fluid flowing through this non-uniform pipe, non-uniform tube, then the speed of water not same at both ends. The speed of water at point region C and region D not same, they are different. This can be understood with the help of Bernoulli's principle and Bernoulli's equation. Let A1 be the area cross section of C region and A2 be the area cross section of D region. Let V1 be the speed of liquid at lower region C and V2 be the speed of liquid at upper region D. And also let the P1 be the pressure of the fluid at lower part and P2 be the pressure of fluid at upper part. As we said, V1 be the speed of liquid at lower region. In time dt, this liquid at lower part will travel to some other place, that is from C to E region, in this region. At the same time, in the upper part, the liquid will travel from D to GH region. So this is the region. Here the liquid will travel in time dt. In time dt, as the liquid is flowing from C to EF in the lower part and D to GH in the upper part. In both cases, the liquid transported from C to EF and D to GH will remain the same. That is, volume of liquid transferred from one section to another section inside the tube in time dt remain the same. In lower part, the liquid is traveling through a distance d1 in time dt. In upper part, the fluid or liquid that is traveling a distance d2 in time dt. That is, amount of fluid, that is the volume of the fluid passing through cross section A1, A2 through distances d1 and d2 remain the same. So here is the volume dV passing, as well as in the upper section the amount of, that is the volume of the liquid passing is the dV, will remain the same. Since volume is given by area of cross section multiplied by length of liquid flow in time dt, therefore at lower end the volume of liquid flowing in time dt is given by A1 multiplied by d1. Similarly, the volume of liquid flowing in upper section from D to GH region is equals to A2 multiplied by D2. But the amount of volume flowing in time dt remains the same. Therefore, A1 d1 equals to A2 d2. Call it equation number 1. Since pressure equals to force divided by area, therefore force equals to product of pressure multiplied by area. Therefore, at lower end, the force F1 equals to pressure P1 multiplied by cross section A1. Similarly, at the upper part, force F2, force due to the liquid flow, F2 equals to P2 multiplied by area of cross section A2. At lower part, the liquid is moving through distance d1. Therefore, work done at lower part W1 equals to F1 multiplied by d1. And at upper part, liquid is moving through distance d2 from d to g. And work done W equals to F2, magnitude of work done F2 multiplied by d2. W2, we place here negative sign. Why negative sign? Negative sign is because the force at D opposes the displacement of liquid. Therefore, the work done is negative here. Now, net work done W equals to F1 D1 plus minus F2 D2. That is equals to F1 D1 minus F2 D2. Call it equation number 2. Now, putting the values of F1 equals to P1 multiplied by A1 and F2 equals to P2 multiplied by A2. So, W equals to F1 nothing but P1 multiplied by A1 multiplied by D1 minus F2 P2 A2 multiplied by D2. Call it equation number 3. But A1 D1 nothing but area multiplied by length, that is equals to volume. As I already told you, both volumes are equal. A1 D1 equals to A2 D2, already we established, that equals to dV. Therefore, W equals to P into dV minus P1 into dV minus P2 into dV. So we can take dV common. This can be further simplified. W equals to, taken dV common, P1 minus P2. Or this can also be written as P1 minus P2 multiplied by dV, one and the same. Call it equation number 4. This work done is also equal to change in mechanical energy. So work done equals to change in mechanical energy, which is nothing but change in the value of kinetic energy plus change in the value of gravitational potential energy. Therefore, W equals to delta KE plus delta PE. At the lower end, the velocity of the liquid is V1, and at the upper end, the velocity of the fluid flowing is V2. And here is the kinetic energy given by half m V1 square, and at upper end, the kinetic energy is given by half m V2 square. Now, how to find out the mass of the fluid flowing in this region in a given time dt? So in this region, how much mass of the liquid flowing? Because we need to find kinetic energy, and kinetic energy formula is half mv square. So we need to find mass of the liquid. So mass of the liquid is given by density multiplied by volume. Therefore, m equals to rho v. This we can utilize to find out kinetic energy of the liquid. Therefore, kinetic energy at lower end equals to half m1, that is rho dou v v1 square, and kinetic energy at upper end, that is at region D, is given by half m2, nothing but rho v v2 square. Therefore, change in the kinetic energy delta KE equals to kinetic energy at upper region, that is half rho dV multiplied by v2 square minus half rho dV multiplied by v1 square. This dV nothing but change in volume, and this v nothing but velocity. Be careful here, both are v, so don't confuse yourself. v1 and v2 are velocities, and dV nothing but change in the volume. Therefore, change in kinetic energy equals to half taken common, rho dV taken common, we get v2 square minus v1 square. Call it expression number 5. Now we need to find out change in the potential energy. Potential energy is given by the formula mgh. This is a gravitational potential energy. So region C is at a height h1 compared to the ground. So this is mgh1, that is the gravitational potential energy at point C, and gravitational potential energy at region D is given by mgh2. M is nothing but mass. Mass we already having, that is m equals to rho into dV. Therefore, at point C, the gravitational potential energy PE1 is equals to mgh1, that is equals to rho dV multiplied by G multiplied by h1. Similarly, potential energy at D gravitational potential energy at D, let us call it as a PE2, that is equals to rho dV multiplied by G multiplied by H2, where H1 H2 are nothing but height of the region C and D from the horizontal reference point, reference level. Therefore, change in potential energy equals to PE2 minus PE1, that is equals to rho dV G H2 minus rho dV G H1. Now we can take common rho dV as well as G in bracket. It is H2 minus H1. Call it equation number 6. But W equals to change in kinetic energy plus change in potential energy. Therefore, work done is equals to addition of equation 5 plus equation 6, that is equals to W equals to half rho dV V2 square minus V1 square plus rho dVg multiplied by H2 minus H1. Call this as a expression number 7, and we already have another expression for work done given by equation 4. Both are the same. Both equation 4 and 7 give us the same result. Therefore, comparing now equation 4 and equation 7. So after comparing equation 4 and equation 7, we can take dV common in RHS part. So half, even rho can be taken common. So half V2 square minus V1 square plus G multiplied by H2 minus H1. In left side we have P1 minus P2 multiplied by dV, cancelling dV both sides. So we get P1 minus P2 equals to half rho V2 square minus V1 square plus rho multiplied by G multiplied by H2 minus H1. This equation is known as Bernoulli's equation. Now, opening all brackets at RHS side, half rho V2 square minus half rho V1 square plus rho G H2 minus rho G H1. Now bringing all the terms with suffix 1 to the LHS side. So that is P1 and this term plus half rho V1 square and this term plus rho G H1, and writing all the terms with suffix 2 at RHS side. So that is P2 plus this term half rho V2 square and this term plus rho G H2. Call it expression number 8. From this relation, from this equation number 8, the LHS part correspond to lower region of the pipe and the RHS part correspond to the upper region of the pipe or tubular section. From this relationship, we can generalize this equation number 8. That is, instead of writing suffix 1 and suffix 2, we can generalize it as P plus half rho V square plus rho GH equals to constant. So now after all this discussion, let us define Bernoulli's theorem. Bernoulli's theorem, there are the three parts. One is the pressure energy, another is the kinetic energy, another is the potential energy. Addition of all these energies is always constant. That is the Bernoulli's theorem. So on the basis of above calculation, on the basis of above discussion, now we come to define Bernoulli's theorem. Let us state the Bernoulli's theorem. Bernoulli's theorem states that the sum of pressure energy, so P is the pressure energy, and changes in the kinetic energy per unit volume. That is important. Changes in kinetic energy per unit volume. Everything we are taking per unit volume here. So once again, it states that sum of pressure energy and changes in the kinetic energy of moving liquid per unit volume and changes in potential energy of liquid per unit volume that occur during the flow of liquid. The liquid is flowing from one end to another end. In that case, the addition of all these three energy is equals to constant. This remain constant. So this is nothing but the Bernoulli's theorem. I hope you got what is Bernoulli's theorem. If you got it, then please like, share and subscribe the channel. Meet you again with next topic. Till then, wish you good luck. All the best.